our project, I kind of introduced it a little bit during the last presentation I made, but this one's it's a bit different. So here we have the same general goals of wanting to take this vibration data and collect it, but the method that we're using to do it is very different. So this one's specifically for modeling the rockets and for eventual course control. So just a really quick overview. We'll go through the introduction, talk about what the goals for this project in particularly were, the modules that we developed to get this job done, as well as some simulations and actual results. And that Geosensor application should not be there. I apologize. Good. So as an introduction, fairly similar to the other one, these vibration characteristics can be very important for modeling a rocket or any kind of vehicle. We can use this to better model the rocket and therefore make our feedback control systems much more accurate, or at least our simulations for them and then our eventual applications. So some of the motivations behind this. Feedback systems for the most part are generally wired in. Once you decide to make things wireless, you have the addition of delay and noise, which you see there as D and N. So this can drastically affect the feedback control effectiveness, especially if your delays get too high or you have too much noise. And that's pretty basic. But what we want to do is we also want to get rid of those wires though, because they can be quite heavy, especially for much larger rockets. For smaller rockets like the ones we generally use, it's not as big of a deal, but the less space there is, the less you can put on these rocket payloads. And that's one of the things that they want to do is have these rockets that they can send out all the time. They want to put as much test materials as they want on there. So if you're wasting all this space necessary to keep wires separated from everything else, you're losing space for your packages. So we really want. So we use two methods of collecting the data. We have onboard storage. We're using an SD card logger to do that, as well as the wireless network that we have set up. We want to sample this realistically at least 150 samples per second. So that's more of the hardware side of it. But we also, in order to get to that data rate that we want for the size of the packets that we're sending and the method of communication, we need to verify our communication schemes. So this part focuses a little more on the actual wireless communications. For this case, we're using a staggered transmission setup. So and the other thing is that we built our own boards. The previous projects that I talked about, they used telespeeds, and we want something that gives us a little more freedom of control. So something we could modify very easily and not have to worry about learning SIE to write code, since it's not a very popular language. That's the goal though. Right.
So here's a block diagram of each of the nodes. So as you see, we have just AA batteries powering all of this. The whole system uses 3.3 volts, so we have 3.3 volt regulators on each of the boards. And the microcontroller we're using is a PIC18F4680, and just runs C code on it. And we're using serial communication to write to both the SD card and to the XB radio. We just have them connected in parallel, and anything that the XB radio receives, the SD card receives as well, and stores it in a text file that we can then remove the micro SD card from the node and put it into a laptop and open up the text file and see all the data that was collected by that node. And all the data is read off a 3-axis accelerometer, simple analog to digital conversion. It requires three analog to digital conversions per sensor because there are 3 different axes. So yeah, that's pretty much it. This is a little diagram to show how our timing is set up on each of the nodes. We have 3 nodes, and we name them top, middle, and bottom. and so we just have T, M, and B to signify top, middle, and bottom. And what we have is we have the top node. We have all of them do the A to C at the same time, so that we can read the data. So that all the data is taken at the same time. That's pretty crucial part of this. But and then we have the top node send, and while the top node's sending, the other nodes are doing nothing. And then we have a small buffer in between that and the time when the middle node sends, so that we don't get collision between packets. And all this is set up so that we don't get collision.
Or have less.
Yeah, as little as possible. Our timing schemes are slightly off because of the delay functions that I was using aren't extremely accurate. So something needs to be done about that for next round of.
So how many samples do you take for one period of sensing? Just one, or?
Oh, no.
Lots of them?
One at a time. So that A to C is one sample. Transmit the sample.
Oh wow.
Sample again.
But then you have a huge delay with because you stagger them.
Right.
To communicate
right.
them.
You have to wait. You have to wait for the other nodes to transmit their data before you can transmit again.
The actual transmission time period is actually like 2.5 milliseconds. But the reason why it's so long isn't because of the radio at all. It's because the way we have it set up, we're using serial communication between two nodes at I think 19.2K baud. So for the number of bytes that we want to send, it's pretty slow, and that's our bottleneck is the communication between the microcontroller and the radio. So the radio itself has ADCs on it, but I don't think it has enough. Or what was the other reason? It was either the resolution or something like that. They weren't really accurate. We had another person in our lab work with them, have difficulties with the ADCs. So the best thing to do is to use a microcontroller, but we need to find a better way to communicate with them. So
that is why our simulation would show better performance compared to this.
There's just some specifications. Like we said before, 19200 is serial communication baud rate, and our sample rate is 150 samples per second. Unfortunately, we had to slow it down a little bit in order for our MATLAB code to keep up with it. And in the demo, we're going to show you. We'll show like a live testing of. It'll actually show all of the acceleration data from all the sensors at one time, but it was jamming up MATLAB, so there's too many.
Alright, so this time, last time I presented Opnet, I didn't talk about this node. Opnet has the latest version of Opnet has Zigbee protocol added to IE AO2.15.4. The Zigbee protocol had the IE 2.15.4 has a physical and a MAC layer, and the network layer, if you see that, and the application layer is the Zigbee that is added on top of the standard, which is the Zigbee standard. So last time I didn't show this. This transmits. This receives the data in the physical layer. This is the MAC layer that does the CSMA, as you're familiar with. We don't do CSMA here, and that's a major difference between simulation and here. You guys are familiar with CSMA, right? So one sends at a time, then the other one sends, right? So here we do timing. Here we do CSMA, and the network does the routing part. For example, if you do star topology or mesh topology or tree topology, and the application layer just generates traffic and receives. For the specification of each node, we had 3 end nodes and 1 coordinator. The top node acts as a coordinator to coordinate all these nodes, and the 3 nodes will send traffic to the coordinator, which is the last one. And they're using the star topology here, so basically the coordinator will be our kind of switch. And we have physical layer parameters, so it shows you the receiver sensitivity up here, which is minus 85 dBm, and your transmission bands we have here. It shows you that we're operating in the 2.4 gigahertz, frequency band enabled up there, 2.4, and also the other ones we disable because we're using the 2.4, and we have a transmitter power of 0.05 watts, and then also we have here, this is a network parameter, so if you can have an option of, let me just open this again so that you can see it better. If you see the network parameters here, you can see that here you can see that you can enable tree, star, and mesh. Here we're using a star topology for this configuration, and well, pan IDs for each network they use different pan. If you have different networks, they use different pan IDs, right? And we have the application traffic here. We generate the traffic with a packet size of 40 bits constant, and so basically our samples here, because we matched the simulation to this because we're generating 20 samples per second here, 20 packets per second, right?
For the demo, yeah.
For a demo, but for the real time it's 150. So we try to see what's the difference between those two as well. So we did also a difference between star, mesh, and the other one, tree, but it doesn't make much difference for low amount of traffic. But when you have, if let's say your distances are higher, like if they're further away from each other and they're using much more traffic, it makes more difference in the real. But for our application, the three ones work the same way.
I mean, is it realistic to have just 3 sensors on like a huge rocket like that? How many are you planning to have?
We're planning on having 5.
5?
Yeah.
Yeah, they want one every 3 feet. That's what it is. So
Also,
about
the
15.
rockets are the same that you presented last time? The size of them, or
That's-
different type of rocket?
That's a different size.
Okay.
That one was smaller.
Okay,
But it had a different engine as well. I mean, it was,
okay. But it's not like this one that you showed in the picture, right?
right. Yeah.
Oh, no, no, no.
Yeah, they've got like.
That was for wow factor.
Yeah. They got like 4
That
or 5
was an
strong.
Orion? The one they haven't built yet?
Yeah, right.
Alright, so just very quickly, we just run this. The coordinator first starts to send a bunch of signals to match all of these nodes together. It takes a couple seconds to all of them to be matched together and join the network. The top node is the coordinator, and the last 3 ones are the sending nodes. So after a couple seconds, I'm going to go faster. Once they get the channel matched, now they're still matching. That's why the traffic was going up. It wasn't constant. For the first few seconds, you don't see a flat line of traffic. Okay, now that if you see that now they're matched now, and now they're sending the packets all the way to the coordinator from all the 3 other nodes. And
I'll move this out a little bit. Alright. Hey, go ahead. Maximize that maybe? Go ahead and give it a. So I mean it's a slight delay after a while, but as this goes on, it's
As you
getting
can see,
slower and slower.
the Z direction is this way, so you can
Okay.
see the Z direction is getting the most, and the top node is getting the most vibration as opposed to the other ones. This one's obviously getting the least because it's shaking the least, and then the middle, somewhere in the middle. But if you move it to the side, you'll be able to see Y and X direction. Or
Now
Y
once it
direction
hits 1,000
changing.
samples, it slows down a lot.
Oh,
'Cause
really?
It's got to try to regraph 9,000 plus points. I just
Yeah,
usually
can you
kill it.
maximize it so we can actually
Well, I
see
mean
it?
it's done now.
Mm.